MCV4U1 Chapter 4 Curve Sketching Session 5. In this session we are going to work on critical points, local maximum and local minimum of a function. We know when derivative of a function at a point is 0 or does not exist, that point is called a critical point. By looking at the graph of this function, we'll see C and f of C is a local minimum. F prime of C is 0. For x's near C and less than C, the derivative is negative. Slope of tangent line is negative, therefore the derivative is negative. And for x greater than C and near C, derivative is positive. Similarly, we can talk about local maximum. When moving left to right through x values, if f prime of x changes sign from negative to positive at x equals c, then f of x has a local minimum at this point. If f prime of x changes sign from positive to negative at x equals c, then f of x has a local maximum at this point. F prime of c equals 0 may imply something other than existence of maximum or minimum at x equals c. Example 1. For the function f of x equals x4 minus 8x3 plus 18x2, determine all critical numbers. Determine whether each of these value of x gives a local maximum or local minimum or neither. We find the derivative of the function. Derivative of x4 is 4x3, derivative of 8x3 is 24x2, and derivative of 18x2 is 36x. If we apply addition subtraction rule for derivative, the derivative would be 4x3 minus 24x2 plus 36x. For x is common factor, and x2 minus 6x plus 9 is x minus 3 to the power of 2. If we set derivative to 0, we have x equals 0 or x equals 3. Derivative is negative when x is less than 0, between 0 and 3 it is positive, and more than 3 it's also positive. For x less than 0, the function is decreasing. Greater than 0, less than 3, it is increasing. More than 3, it is also increasing. Since the derivative changes sign at 0, it is local maximum or minimum. From negative to positive means it is local minimum. The graph of the function is sketched in this diagram here. We see at 0 we have local minimum, and that's the only extrema that we have. Next example. If we consider function f of x equals x3, derivative is 0 at x equals 0, but the sign of derivative does not change, therefore it is not local maximum or minimum. Derivative 0 means the tangent line is horizontal. The importance of this point is the tangent line is passing through the curve. If we consider the function f of x equals cube root of x plus 2 to the power of 2, the derivative of the function is 2 over 3 times x plus 2 to the power of 1 over 3. The sign of derivative is changing at x equals -2, but derivative is undefined at -2. We have a vertical tangent line at -2. Since the sign of derivative is changing at -2, -2 corresponds to a local extrema. It's changing from negative to positive, therefore it is a local minimum. In one of the examples or exercises we had before, we talk about the graph of y equals absolute value of x minus 2, and we saw a 2 and 0 derivative does not exist, but it is a local minimum. It's good to put these two examples, either x plus 2 or x minus 2, beside each other and see at both of them we have local, which is absolute minimum, but derivative does not exist. Let's be clear about critical numbers and local extrema. The critical number c determines the location of a local minimum value for a function if f of c is smaller than f of x for all values x near c. And a critical number for function f is a point like c when either f prime of c is 0 or f prime of c does not exist. Similarly, the critical number c determines the location of a local maximum when f of c is greater than f of x for all values of x near c. Together, local maximum minimum values of a function are called local extrema. If we look at the graph of cube root of x plus 2 to the power of 2, we see for x's near -2, f of -2 is smaller than f of x. Next example, given the graph of a polynomial function, sketch the graph of the derivative. By looking at this graph, we see we have a cubic function whose leading coefficient is negative. So one thing that we know is the graph of the derivative is a quadratic function whose leading coefficient is negative. That means the derivative is, the graph of the derivative is the graph of a quadratic function, a parabola, which is downward. Before 0, derivative is negative. Between 0 and 1, derivative is positive. And after 1, derivative is negative. At 0 and 1, derivative is 0. At 0 and 1, derivative is 0. Before 0, negative. After 1, negative. And between 0 and 1, positive. By looking at the graph of the function, we see at 1/2 and 2/3, the derivative is maximum. To understand this better, we need to know the meaning of point of inflection, and we talk about that later. But here we can say the rate of change of derivative before 1 over 2 is positive. That means derivative is increasing, and after 1 over 2 it is decreasing. We'll see it is going to be the form of the function. If the function is in this form, the derivative is increasing, and you see the slope of the tangent line is increasing, and if it is in the other form, the derivative is decreasing from positive to negative, from positive to 0 to negative. In summary, for a function f of x, a critical number is a number c in the domain of the function when either f prime of c is 0 or f prime of c does not exist. It's not defined. As a result, c and f of c is called a critical point and usually corresponds to local or absolute extrema. Not always, usually. First derivative test. If f prime of x changes from negative to positive at c, c and f of c is local minimum of f. If f prime of x changes from positive to negative at c, then c and f of c is local maximum of the graph. If f prime of x doesn't change the sign at c, then c and f of c is neither a local maximum or a local minimum. So far, what we learned about curve sketching is summarized in this algorithm. We find critical numbers of a function when derivative is 0 or does not exist, and then use the first derivative to analyze whether f is increasing or decreasing on either side of each critical point. Based upon our finding in step 2, conclude whether each critical number locates a local maximum or a local minimum for the function f, or neither. Next session, we are working on question number 2, question number 3, part B, question 7, part B, and question 10 on page 178 and 179 of the textbook. Thanks for watching.